Okay, we've got simultaneous equations, two equations, three unknowns, but we're not being asked to solve them. In fact, there's an infinite number of solutions. You could just sort of pick some numbers like x is 2, y is 2, and then z is 3. That would work. Or x is 1, y is 3, and z is 4. There's an infinite number, but we're not interested in that. What we're interested in is the total of x, y, and z, and then subsequently to find the minimum possible value of this total. So right, here we go. We got, this is absolutely crucial, this little bit up here. X is less than or equal to y, which is less than or equal to z. So since x is less than or equal to y, the maximum value of x is going to actually be y. Because it can't be, it can't be, well, if it's smaller, then it's smaller, but it can't be any bigger than y is what I'm trying to say. The max value of x is y. And when x equals y, we're going to get 2x equal to 4, so x is equal to 2. Therefore, x has to be less than or equal to 2. Okay, if the maximum value is 2, it has to be less than or equal to 2. So I've dealt with that bit there. Then next up, I've got show that t equals 11 minus y. Well, I could add these up. X plus y plus y plus z is equal to 11. And therefore, if this is t, therefore t plus y, because I've got my x plus y plus z, is equal to 11. And this implies that t equals 11 minus y. Okay, and I've shown that bit as well. Nice. Now, find the minimum possible value of t, giving one example of x, y, and z where this occurs. Okay, so what we need to do to get the minimum value of y is to maximize, sorry, the minimum value of t is to maximize y. And what we can use a similar idea to what we did. We maximized x in the first part, basically. It has to, the biggest it could be would be 2. So we can do a similar idea here. Since y is less than or equal to z, the max value of y is z. So when y equals z, we're going to get 2y is equal to 7. So y is equal to 7 over 2, or 3.5. And that's going to be the maximum value then. So therefore, so I could write down that therefore y is less than or equal to 3.5. So therefore, the minimum value of t is 11 minus this 3.5, which is going to be 7.5. And it's going to be when y equals 3.5. So that is going to mean that x is going to be 0.5 because they have to add to give 4. And z is going to equal 3.5. So we've shown that there is a solution that works. And yeah, that's it really. That is our answer for this first part. Okay, second part, we've now got 5 unknowns and 3 equations. But remember, we're not trying to solve it. We're actually going to be trying to add A, B, C, D, E together to give S and then find the minimum value for it. So the first thing I did when I did this question actually is I added them all together. I just thought, yeah, I'm going to add them all together, but actually you just end up with too much. So that's not the way to go. Instead, you want to add up just the first and the third. So A plus B plus 2C plus D plus E is equal to 13. And this implies that S plus C, there's an extra C there, is 13. So S equals 13 minus C. And to minimize S, we must try to maximize C. Now, I do this question with the benefit of hindsight. We're going to see there's a bit of a problem in a minute if when you do a certain thing to try to maximize C. But that's going to sort of be the starting point. And therefore, this is the path that I went down at this point. I said that C is less than or equal to D, which is less than or equal to E. So the max value of C is C equals D equals E. And this implies that 3C is equal to 9. I've just replaced D and E by C up here when they're the same. And so C is equal to 3. And therefore, min value of S is surely 10. Okay, and job done. Or is it? Because, when I did this, I thought, there's no way this is worth 8 marks, isn't it? We're just using the same method from before. And if you put it back in, we'll see that it doesn't work. So we basically have got when C equals 3, D equals 3, E equals 3. There's no problem with that. And when we put it back in, because C and D are going to be 3, that's going to get 6, and B is going to have to be -1. Okay, no problem with that. But now when I put B as -1 back in, I've got -1 plus 3, that's going to be 2, so A has to be 2. That's not okay. Because remember, A is the smallest one. So that's where I'm coming back to at this point. To minimize S, we must try to maximize C. But we can now add but satisfy the equations. It's not, actually, whilst C can equal, wait, no, C can't equal 3 because you just then don't get this inequality holding. And yeah, actually, I even take that back. Satisfy the inequalities. There's no problem satisfying the equations, but we need to satisfy the inequality above. Okay, so yes, there is a bit more to this problem. Okay, that's fine. So time for a bit of a rethink. Okay, this is not meant to be a completely polished solution. I'm trying to show you sort of my solution method for this problem. So I kind of looked at some of the equations and I thought, you know what, I can very quickly subtract them to eliminate some of the unknowns. So if I do the bottom one minus the top one, then I'm going to get E minus B equals 4. And okay, I have to show full written solutions, so I'm gonna make sure I make this clear. So I've got C plus D plus E is 9, and B plus C plus D is 5. So subtract, and these are going to cancel, these are going to cancel. I'm left with E minus B equals 4. So what that means is that E must equal B plus 4. Okay, we've now got like a restriction basically between E and B. And I can do the same with the other one, the other two. It's not really going to help if I do the top and the bottom one because there's too many, there's only the C's there the same. Or maybe it will help, but it seems best at first to do these two. So B plus C plus D is 5. And then A plus B plus C is 4. Okay, subtract them. I get D minus A is 1. Right, now this is interesting. That means that D is actually equal to a plus 1. Right, that is a restriction we have. And it's quite a significant one. Like E being 4 more than B didn't seem too bad, but actually D is only allowed to be 1 more than A, which kind of tells you, look, it's the fourth largest, but it's only 1 more than A. All right, brilliant. All right, let's get back to this inequality. So A less than or equal to B less than or equal to C, so on, implies that A is less than or equal to B, which is less than or equal to C, which is less than or equal to A plus 1, which is less than or equal to B plus 4. So C can also only be 1 more than A, actually. So max value of C, because remember, that's what we're trying to do. We're trying to maximize C to minimize S, is A plus 1. And that means if we come back to the first equation, this one here, we can replace C by A plus 1. So when this occurs, A plus B plus A plus 1 is equal to 4. So I'm going a bit slow here, I'm just making sure I get it all right. So then 2A plus B is equal to 3. And now we basically, to maximize, we want to also maximize A then. We want to maximize A, which will occur when A equals B. So then we're going to get 3A equals 3 and A equals 1. And therefore, B equals 1 because it's the same. C will equal 2 because it's 1 more. D will equal 2. And E, remember, was 4 more than B. So it will equal 5. And let's just check the equations. Okay, so we've got 1 plus 1 plus 2 is 4. That one checks out. 1 plus 2 plus 2 is 5. That one checks out. And 2 plus 2 plus 5 is 9. That one checks out. The equations hold. So actually C equals 2 is the maximum value of C such that the inequalities hold and the equations hold, I guess, is what we want to say. Equations hold. And therefore, the minimum value of S, don't forget that's what we're asked for, is all the way back up here. Remember, S was 13 minus C, so it's going to be 11, so 11 is actually achievable. Okay, really nice question. Bit different, isn't it? And but yeah, working through these sorts of ideas, yeah, really good. Okay, well done. Just a quick discussion about the official answers, actually. They decide to look at the bounds for x in the first part rather than just looking at the maximum value. I don't think you really need to look at the minimum value, but I suppose it doesn't hurt, and why not? But I just focused on 2. So they get the same answer here, and then they construct a similar sort of thing here to what I did, but then yeah, actually they then jump to c being less than or equal to a plus 1, which I took a little bit of time to get to, um, but it is a very similar method. And I just want to say, like, I wouldn't have thought to do it like this. You can use a graphical method by rearranging. Do you know what? I haven't completely got my head around this, but I'm just going to show you because I think it's good to discuss these things and I should spend a bit of time on it. But you can plot some of these graphs, C against A, different inequalities, and actually get a little region here and then the maximum value. I don't know, that seems harder to be honest, but it nicely does relate to this topic of linear programming, which you might want to look into. Anyway, that's it. Thanks.